Spoiling myself.
Hey everyone! Oh my gosh, 2 hours later and I'm gone. Where am I? Please tell me the camera's working. Oh no, wait. Is the camera? Oh no. No. I should have checked the camera. Let me try to reset. Let me put a little music on here while we try to fix this. I'm gonna go without a camera today. Hey Jesse, hey Sheena, hey Adam, good to see you here. Let me try resetting the camera, okay? Turn camera off, be right back. Try to reset. Okay, I just reset the camera. Da. Can't reset OBS right now. Let me go to camera green screen. What happens if I go? I should not have done that. Showing OBS virtual camera now. We don't want it on OBS virtual camera. Let me try that again. All right, we'll get to working some problems here in a second. I should not have made that change. It does this sometimes when I reset. Well, I feel like we should take a picture of Brian and just put him down there in the corner. Here, wait. Let me go here. 1 second. All right, we're going to do something. 2 seconds. And then we'll do some Chapter 17 problems. Okay. Go see that Brian image. All right, there goes that. Plus Brian image. Okay, browse. Look at that. There I am in the corner now. Doing some cross validation in Python. Do you know why I'd be getting a too many splits for sample size error? Good question, Adam, right there. There's me in the corner right there. That's me in the corner. Spotlight. Let's go head over here and do some Chapter 17 problems. Which ones do you want to do, Jesse? I have to reset before my next stream right here. But for now, we will just do the following. Which Chapter 17 problems should we do? Chapter 17 problems. Yeah, which one on Chapter 17 homework do you want to do, Sheena? Name it and we shall do it. Sometimes, I don't know why it is. Sometimes the camera just doesn't play nice. And then right now, yeah, it's doing that. It's saying OBS virtual camera because I switched to that hoping it would fix it. But it's not fixing it. Maybe I should turn off the camera again. Let's see. The one says, well, we've done that one a few times. We could do the man who moves to a new city. We did it yesterday. We can do it again here. Assignment manager, chapter 17 homework. Let me open up Word. Sorry, I reset the computer today, and apparently that was a horrible idea. Hence why I don't reset the computer much. If everything's streaming fine, sometimes I just say, you know, everything's working fine. Don't reset your computer. Never close down browsers. Have 60 Word documents open. That is the way to do it. All the Word documents. And we'll be started here in one moment. Crazy start right there. That's why we don't close the computer down. A man who moves to a new city. We could do that one, though. That's the one people want. So we do what people ask right here. So if you're watching this right now, swing by, ask any questions you want, and we can work on it. Could we do the consumer spend more on a trip to Walmart or Target? Yeah? Mm-hmm. Drinking glass? Good stuff. Let's work on all these right here. You know what we might do? We might just do the homework from the start to the finish. How's that sound? Like just working on each homework problem from the start to the finish. I'm going to keep that one open right there. I think that might be also Jesse's as well. How does this sound if we work on, I think we could do the whole thing. We've got enough time here today. We could, well, so the homework, I think, is the quiz. The quiz has it. This is on the quiz right here. Agree with Jesse. You want to do the quiz? Can we do the quiz? We can work on, so let's work on the quiz on every question we can. Working on quiz from start to finish. I've already done the homework. Awesome. Okay, let's work on every quiz question we can. Okay, let me get the quiz up and going right here. We'll work on every single quiz question. Every single quiz question we can. No camera today, apparently. Never reset your computer. Okay. Actually, I think the first one we have right here is the Walmart and Target one. So let's go ahead and do that right here. Okay, do customers spend more? So Stat Tool 1, Chapter 17 quiz. Do consumers spend more? Okay, so there might be multiple versions of this question, but let's see what it's asking right here. And first thing you notice right here is we get what to start. What do we have to start with this? There's a picture of me. What do we have to start with this? You immediately notice the what. We have to know what we have right here. Like, what is going on with all of this right here? What is the point of that? What is it? So we have to be like, okay, what does this mean? What does that mean? A table of info and notation. So what does this value mean right here? What would you say that value is? So what are they telling us with 45 right there? What does that value mean? So the important thing to know is sometimes we have to mark the notation ourselves, and other times we have to, it gives us the notation, and then we have to put it into the equations. So what does the value of 45 mean right there? Like if you had to explain someone in words, they're telling you what? What would the 45 mean in words right there? This is where we can solve other problems, because remember, we're not just trying to solve this problem. We're trying to learn the steps of solving it. And the key thing here is knowing the components of each problem. And this is called the two sample T. So there's two samples. The two samples of the two sample T would be here and here. There's the two samples, meaning two groups. So there's a two sample T. And T is going to be because it's a quantitative Y variable. And so that's where we get the mean. And what does the 45 represent for 1,000 points? Let's go crazy on those points. What does the 45 mean to us? There's a hint. What does it mean? What does the value of 45 mean in that table? How would you explain that to someone if you had to write it out? You'd say the value of 45 represents basically. So 45 is the average amount spent by the 85 target customers. So great job, Jesse, right there. 45 is the average for the target customers, and there was 85 target customers. And then the variation, which is the standard deviation, is 20 for this right here. Same thing could be said for Walmart customers, that the average amount meant, no worries. Good to see you here, Mary. The average amount spent among the 81 Walmart customers was $51 with a standard deviation of 18. So understanding that right there. Now, it says the interval for this is negative $11.84 to negative 0.16. Now, notice what is at the direct center of this interval. So we can do some equations right here to see how this works. And it's going to be there's the equation. So think about with what we have right here. what is going to be the estimate of the difference? The estimate, oh, it's Walmart minus Target. Oops. The computer's possessed. Really? It's changing it on me. Computer's possessed or something weird. What is the estimate? Oh my God. We're going to reset the computer again after this. What is the estimate of the difference? What is the estimate of the difference? The estimate of the difference would be what right here? So take a look at this information right there. And the estimate of the difference would be what? And so what is that equal to? The estimate of the difference would be what? I updated the computer and everything. Should have done it. Yep. And then take a look. That gives you, and actually it's Target minus Walmart. I keep doing it the wrong way right there. It should have been Target minus Walmart. And it's 6. They actually did it with -6. So if you notice, Walmart is higher. So it would be Target minus Walmart. I did write the first way. So I guess we could go back and rewind time a little bit. It is apparently Target minus Walmart. So -6. Exactly. And that's the center of the interval. So then can you then figure out the margin of error? And we can estimate the margin of error pretty quickly because if it's -6, the margin of error is kind of about plus or minus what? So it doesn't ask us these questions, but the margin of error is very close to what? See, it almost goes to 0 and it almost goes to 12. So the margin of error, if you think about the interval, it's not quite this, but the margin of error of the interval would be 6 plus or minus 5 point, and let's go see what it says again for the interval, 84. And then we could check our work, and it's technically -6, depending on how we want to interpret the interval. But that is the interval right there. So the interval is -6 plus or minus 5.84. And it's important to see these components right here. And we could even go further with the t and other information to figure out what the standard error is and backwork this problem. But there's the information it's giving. There's some interpretations. Does that make sense, Jesse, right there? That we can understand that this is the interval. The estimate would have been -6. That's at the center of the interval. And you can also see it over here with 45 minus 51. Yep. And so what does this mean? We are, or I am, 95% confident the mean purchase amounts and the difference between Target and Walmart is between, so Target is this much less than the mean of Walmart. That they should say true mean. I'd prefer they say that. And Target is less by this amount. The mean purchase amount of Target is between this much less than the mean purchase at Walmart. So that should be right there. Oh, was that the whole question? Oh, there we go. I think there's another, do customers spend more? We'll try to find that other, do customers spend more? Because I think there's longer versions of this. Here we go. So this time we're actually running the hypothesis test. So I kind of like this because the first one right there was a confidence interval, and the second one is a hypothesis test right here. So the equation is going to be slightly different. But I do want to point out the similarities between what you're doing. If you look at the confidence interval versus, there is something really weird about this because I cannot, it's changing my pen when I go up there. We're going to open a new Word document. Pretend that Word document's not going crazy. So we have Y bar Walmart minus Y bar Target. I believe that's the way they're doing it. Plus or minus the T statistic with 2 complicated degrees of freedom. Star because we pick it based on the level of confidence. And then the standard error is S sub Walmart squared over N sub Walmart plus S sub Target squared over N sub Target. Now, what's important to know is that this quantity right here is known as the standard error. So you can call it standard error the difference or the standard error y bar 1 minus y bar 2. So when you look at the test right here, the test is done very similarly. The test is going to solve for a t with the 2 complicated degrees of freedom, where we have y bar Walmart. We're going to double check the way it solves it, minus y bar Target over, and you can just abbreviate the standard error of the difference. Now, it's important to remember, it's working again, that is the quantity over there, standard error of the difference. Still calculated the same way, but I'm just putting it right there color-coded. It's the same thing. So you can look at the parts of this where you see similarities, where we're doing a t, but those are different t's. We have the difference right here. We have the difference here and the standard error. That's why tests and intervals come to the same conclusions, because they have a lot of the same components, and they can reach the same conclusions using intervals to check values or tests to test values. So when we do this right here for this question, we need to take the notation. Now, I believe we are doing Target minus Walmart. That's what we just decided on the previous one, right? I've done this one before, so it's Target minus Walmart. If you do not do the right subtractions, you will not get the right answers. There we go. So with this right here, we just now need to do what? What's the next step for solving this problem? How are we going to get the answer to this problem? How are we going to solve this problem now? What do we need to do now that we know the equation we're doing? What do we need to do? We could go through the steps right here. It might be best to review the methods. It's kind of a jumping to the solve on the problem right here, which is kind of where I go when I'm thinking about these problems, because I usually know the null hypothesis without thinking through it. Like, because I've probably don't, I can't turn on my camera. Nope, still no camera. Hacks. Yeah, let's do that right here. Jesse, great job right there. Let's show you some points. We're going to use the hacks method for solving this, and we're going to completely ignore what they're asking us to do. So the hacks method of solving this right here, if you haven't heard of the hacks method before, it stands for, let's zoom in on this a little bit here. Our hacks method is hypothesis, annotate notation, which we've already got for us right here. There we go. Check conditions, and solve for p-value, which is usually the harder part for people. Good to see you here, Kristen. And so when we do our hypothesis, the first thing we always do in the hypothesis is we give parameter we are testing, then we give the equal sign for the null and hypothesized value. The alternative is going to be almost identical, but we will change the sign to less than, greater than, or not equal to. So a lot of people get stuck on the parameter we are testing part, but there's only 3 options for our class right now. I'm going to leave out one option to see if you can remember the last option. So we could do mu, or we could do something else, or we could do mu1 minus mu2. So what is the last option I've left out that we've been testing? So remember, we are going to test one of these things, the parameter we are testing, the thing we want to understand, the thing we're making statements of truth about. So I left out one of them on here. The only one, well, that's mu. This is mu. That's mu. Mu naught goes over here. So whatever we are hypothesizing, this value over here will either be mu naught, or it'll be another value I'm leaving out, or we usually estimate that this is 0. Now these coincide. Like when we test this, we hypothesize it's this. When we test this, we hypothesize it's this. So the mu naught, not y bar though. Y bar means sample mean. So the sample mean is what we saw in the sample. So we wouldn't hypothesize about the sample because we know the sample. So we have a t-test and a 2-sample t-test. So this is the t-test. This is the 2-sample t-test. And we're missing a one prop or a prop test. So what are we missing right here? Prop test. We'll call it prop test. It's done with the Z. So we're missing what? Oh, no worries. 300 points for that. No worries. P. So if we're testing P, we would hypothesize that P is equal to what? If we're testing P, we would hypothesize that P is equal to what? We would hypothesize that P is equal to what? If we're testing P, we hypothesize that P is equal to what? Because P is the true proportion, so we'd hypothesize that P is equal to what? Not P hat. Good guesses right there. P hat is the sample proportion. We hypothesize that P is equal to the hypothesized proportion. So P hat is the sample proportion, and P naught is the hypothesized proportion. So this is like the hypothesized mean right there. This is the hypothesized proportion, and this is the hypothesized difference between two means. Does that make sense? Like I'm bringing these together. So if in our test right here, we are right here going to be testing the difference between two means. We'll keep this all standardized so we can kind of put the values there. We are going to be testing the difference between two means. So mu1 minus mu2. And we're going to hypothesize that the difference is 0. Yeah, no, and that's why I'm doing this as kind of a review right here, because once again, we're not just trying to solve this problem. This is the majority, except for chi-squared test of independence. This is the way to do all the chapters. This is, I believe, chapter 14/15 or so. Then maybe that's 15. This is about chapter 15. That's maybe 14. And this is 17. I know that. So those are the chapters right there and a review over them. They might be both chapter 15 for... These both might be chapter 15 now. They change the chapter numbers sometimes on us. So that's hypothesis testing in chapter 15. Chapter 17, 2-sample T, which we're doing right now. And then you can see the hypothesized values right there in purple. And then all we have to do is change the sign. So when you think about it, I believe we are testing to see if there's a difference. And this is called the two-sided test. So once again, the reason we focus so much on writing the null is because when we write the null, all we have to do is change the sign to write the alternative. Nothing changes except for the sign right there. So when you look at this right here, notice that the sign is the only thing that changes, because we're going to say as the null that if we were to take the difference between two means, the difference between mean 1 and mean 2 is equal to 0. And the alternative is that the difference between mean 1 and mean 2 is not equal to 0. So this practice right here of writing out the hypothesis is good to know how to do it. And notice how the null has the equal sign. Good solve right there. We're going to do the does not equals for the two-sided. And then they're asking, is there a difference because to see if the two means are equal. So we're testing to see if they're equal. So we'll use the alternative that they're not equal. Now, the good part about this next, hey, Fisa, good to see you here. The good part about this next is we already have all the notation. So we got the notation all right here. The only other thing we're missing is the degrees of freedom, which is going to be super important. Degrees of freedom are 153.96. So let's put that right here. Degrees of freedom equals 153.96. And that's all the notation we need. Now we have to check the conditions. How many conditions do we get for free? How many conditions are there for free? And by free, I mean the ones we can just say really quickly, and then we need to check them. We got 2. We got random. We know we love it. Random, 10%, and then we pause. We pause here because we have to remember what kind of data are we working with. And we are doing the 2-sample T currently. We're doing the 2-sample T. So since we're doing T's, we're dealing with what's. Every time you're doing T's, every time you are dealing with a T right here, you are dealing with what's. By virtue of it being T's, quantitative means. Mr. T is mean if you're doing drugs. So when we have quantitative data, we will have what condition as our third condition? When we have quant, so we say, okay, pause, it's quantitative. So what is our third condition here with quantitative? Now, this is not a condition. It's just us pausing and acknowledging its quantitative data. The third condition for quantitative data is nearly normal. Yeah. Mm-hmm. And then success failure if it was categorical. And then chi-squared is going to be at least 5 expected cell counts. So chi-squared is a little different than our pattern right here, which we just did chi-squared yesterday in class. Then the last condition right here is since there's 2 means, the 2 means need to be what of each other? So in the 2-sample T, the 2 means need to be what of each other? What is the last condition for the 2-sample T right here? The 2 means need to be what of each other? What do the 2 means need to be? Starts with an I. Means that they don't influence each other. The 2 means would need to be what? Great job, Savannah, right there. Nearly normal. The fourth condition, independent means, independent groups. So you can say independent groups, independent means. That means mean 1 does not influence mean 2. And those are the 4 conditions. Now, the solving for the p-value part is usually where people get stuck. Because to solve Long War, yeah, chapter 19. We would probably do some of that. I think we're going to do a lot of chapter 17. We'll get to some chapter 19. Thank you, Taylor, right there. And so with this, and if we should do that, we got more enough time. Yeah, Taylor, remind me, if we don't do that in about 20 minutes, let's go do that one next. Or in about 20 minutes, because we're going to do chapter 17. The T with 2 complicated degrees of freedom is equal to y bar, first mean minus y bar, second mean over square root s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. And this is going to get us the t. The t is not the p-value. The t will be used for that. So we'll grab the notation right here. We'll go down, and we will start putting in the numbers. So we're just going to plug the numbers into this, and that's the key to solving it. It's just being like, okay, we got the numbers, and we have the sample sizes, and then don't make any math errors like Brian. So sample size 1, sample size 2, it's going to be 80 and 79, and standard deviation 1, standard deviation 2. We're just doing target first, 21 and 18. And if I make any errors, please point them out. Mean 1 and mean 2. And so mean 1 is 43. Mean 2 is 51. There's going to be a negative difference of 7. So let's go ahead and solve the standard error right here. The standard error is going to be 21 squared divided by 80. Copy that. 18 squared divided by 79 plus this, and that's going to be close to 3-ish. So we square root that. There we go. And then 43 minus 51, divide by, and we get negative 2.58. Now, here's the thing. I am pretty sure I know the p-value because, and we'll just delete the notation right here. When we draw this t, the t looks a lot like the normal when what? When does the t look a lot like the normal? And we'll show that off here again. Do women spend more on time talking on the phone? Yeah. When does the t start to look a lot like the normal? When does the t basically look like the normal? So we go over here to the t, go to student t, and then when does the t really start to look like the normal? The t starts to look a lot like the normal when the degrees of freedom are really large. After about 50 or 100, like just more degrees of freedom, more normal it looks. So we are here at 153.96 degrees of freedom, which determines the shape. And so once again, they solved this for us in the problem. If you're wondering how we got that value, they told us we could have used the calculator on the site here to put it in, but we don't have to because they give us the answer. We're going to go to find the p-value using the t, because remember, we're trying to find the p-value. Now, here's the thing. We are doing the outside test, and the p-value is going to be very, very close to, it's probably going to be about 0.011. So let's see. Did I get it down to the last decimal? Let's try. We're going to go to outside, and we're going to take the test statistic right there and do the positive version and go outside of it. And there it is. Down to the decimal. 0.011. If we need the fourth decimal, I have no idea too. I didn't know what that would be. But just, I knew it was going to be about 1%. I thought a little bit bigger than 1%. And that's because we need to practice, and I should have done this, drawing the curve. So if you've drawn a lot of these curves, you can often get an idea for what it looks like. And we go right here and we draw a normal curve. Remember, it looks basically normal now. Then we go out here and go 1, 2, 3, and we landed about over here. And then we go 1, 2, 3, and technically we landed on the negative side. But as The Rock would say, it doesn't matter, because we are doing the flip of it. Now, here's a big thing. Why am I graphing both sides right here? Why am I graphing both sides from a t of negative 2.58 and outside of a t of, well, this is just the reverse. We might not want to mark that the t landed there. But why am I graphing the other side too? This is a huge thing you have to know. Why am I graphing both sides? So why are we graphing both sides down here? That's a very important concept. Why did I graph both sides of it? Why did I do the outside? It's the does not equals alternative. That's huge right there. So because the does not equals alternative was picked, the does not equals alternative is going to be the reason that we graph both sides. Less than graphs to the left. So wherever you land, you'd graph to the left. Greater than graphs to the right. So if you do a greater than alternative, you graph to the right. And the does not equals alternative takes and mirror images what you have on the other side of it. It does the outside region. So I think we've got everything answered. They're going to use an alpha of 0.05. So we'll interpret that here in a moment. The test statistic is negative 2.58. Everything should be calculated. 3 decimals, so we would have had it with 3 decimals. State your conclusion. So think about this. Do we reject the null or not reject the null? Our p-value is lower than alpha. My p-value of 0.001011 is lower than my alpha of 0.05. And I highly suggest you practice writing these out right here. So here's the statements. We reject the null. My p-value of 0.011 is less than my alpha of 0.05. This means I reject, I've got everything lined up right here. I reject my null that there is no difference between what people spend at Walmart and Target. I have evidence for my alternative that there is a difference. So we reject the null. There is evidence for the alternative that the two means are not equal. And we got that 100. So really good question right here. But I do want to point out the number one way, and we did a really good solve on this. Chapter 17, homework, question 10. Yeah, I think which one is that, Kristen? It might be in the quiz. If you look right here, this is ideal for learning how to solve these. Using this method and writing these out, being able to say my p-value of 0.011 is less than my alpha of 0.05. This means I reject my null that the difference between these two stores is equal to 0 on what people spend on average. I have evidence of a difference, which is my alternative. Things like that are going to help you out with the test, interpreting it, and there are written interpretations. Let's do the spend more on phones, and then we'll try to do Kristen's next right here. So, sorry for no camera today. Spend more time talking on the phone. Have we covered Canvas content number 10? I don't think we have yet. That'd be a good one too. Spend more time talking on the phone. The core plus mathematics. Where's the phone one? There's the serial one. Classic one. Where is the phone one? There's the man moves to a new city. That one is a favorite. It's a phone one? Jesse said a phone one. Oh, here it is. Okay. So this is spend more time talking on the phone. Then we're going to do Kristen's question next. And I think we're going to jump to Taylor's. Let me mark this in the notes right here. And let's think about the information they're giving us. What do you notice they give in this question? What do you notice they give in this question? They give us a what? They give us a what? In the question, they say, a student collects data from students at her university and reports a 90% confidence interval, and they're taking the difference of the average of men minus the average of women. So when we look at this interval right here, they took data from men and women, and they subtracted the mean of men from their sample, because they're trying to find out the true difference right here. And so with this, we have an estimate of the true difference that it's somewhere between negative 150 to 30. So based on this interval, can it be concluded that women are higher than men? Well, let's think about it theoretically. If the average for men was higher, because we're doing, the interval was created from the sample of men minus the sample of women. If the average for men was higher, it'd be something like 200 minus 100, and the difference would equal what? So this is just idea number one. We're just talking theoretical right here. If men was higher, this is idea one, then the difference would be what? Like, what would the difference be? And this would point to men being higher because men spend on average 200 minutes versus women spending 100 minutes. So the difference here would be what? Be 100, yep. And very importantly, it'd be that. But let's say, and this is just idea number two, these are just theoretical ideas. If the difference were to be something like this, and women had a higher mean, now notice women right here are the second mean, and they are the higher one. Now the difference would be what? What would the difference be? And a good way to remember it is exactly negative 50. So the negative 50 right here indicates that we saw, at least when we subtract this difference here, we'll do the equals. We don't want a minus right there. That the difference was the female mean, the women's mean was 50 higher than the male's mean. So think about this. Our estimate of the true difference contains both what? Yep, chapter 17 right now. Our evidence of the true difference between these means contains both what? Pointer right there and right there. Our interval to estimate the true difference contains negative and positive numbers, and it also contains 0, and 0 might be the true difference. So it might be that women spend up to how much more time on average than men? It might be, so my estimate of the true difference is that it could be that on average women spend blank more time than men. Or I could say I'm 90% confident that it could be that case that women spend up to this much more time than men. So how much more time might it be that women spend than men on the phone? Let's look at the interval right here. Think about how the numbers work. So you want to look at this and think about how the numbers work. It could be the case that women spend up to how much more time on the phone than men? Could be the case, looking at this interval, it could be the case, like I am 90% confident that the true difference between the men's time and women's time on the phone is contained in this interval, where it could be the case that women spend up to this much more time than men. So think about what we have right here. There's a hint. The answer's not negative 50. Look at the context of this, though. It could be the case that women spend up to how much more time on the phone than men? So we're going to look to the interval and be like, what is the interval telling us right here? I'm trying to estimate the true difference between men and women's time they spend on the phone. And it could be the case that women spend, when we estimate the true difference, it could be the case that women spend up to this much more time on the phone than men on average. So what numbers would we use? I am 90% confident that the true difference between men and women, how much time they spend on the phone, is contained in the interval where women might spend up to how much more time than men? What do you think? So remember, the negative number implies evidence the second mean is higher. So the negative, oh, no worries, 100 points are there. So you see, if we get a negative number right here, that is a indication the second mean is higher. So when the interval goes negative, that would be, I am 90% confident that the true difference between the mean time men spend on the phone and women spend on the phone is contained in the interval where women might spend up to 150 more minutes more than men. But it could also be the case that it might be men do what? Men do what? Because remember, there's the positive side of the interval now. The positive side indicates the first mean is higher. So if it is the case that the first mean is higher, the interval contains positive numbers. So it could be the case that men spend up to 30 minutes more. So if you notice, as you interpret this, it goes through 0. Can it be concluded that women have a higher mean than men? No. The interval contains 0, and thus the difference might be women spend up to 150 more minutes more, or men spend 30 minutes more. So the interval going through the positive or negative numbers right here, like this is a theoretical idea right here where the interval came out with an estimate that's positive, or an interval came out with an estimate that's negative, but the interval itself has a margin of error. And when we add the margin of error to it, if the margin of error goes through positive and negative numbers, then we would not have evidence of a difference right there. Does that make sense, Jesse? Like, this is a really good, these are sometimes really short questions, but I want to make sure we talk about the theory and how the interval is created, because once we add a plus or minus on this, like, which of these two intervals right here would indicate a difference? So in this interval, you estimate the difference to be 100. And in the bottom interval, you estimate the difference to be 50. Which of these intervals would indicate to us a difference? Interval 1 or interval 2? Yep. Do some chapter 19? Yeah, definitely. Which of these would indicate a difference? Idea 1 or idea 2? When you did the question I asked about the turning. Which one, Sheena, you want us to do? So which one of these would indicate evidence of a difference? Idea 1 or idea 2? Would interval 1 be evidence of a difference, or interval 2 be evidence of a difference? Which one of these would be evidence of a difference? Which is a good review of the question we just did. Which interval right here, which is the interval 100 plus or minus 110, or negative 50 plus or minus 10, which of those would be evidence of a difference? Man moves to a new city. Which of these intervals is evidence of a difference? So which of these intervals would be evidence of a difference? Would it be idea 1 or idea 2? What do you think? And why? The why is important too, because it's a 50-50 shot. It would be interval 2. So interval 2. So go ahead and tell me what the values are. If you solve interval 2, it's going to be a lower bound of what and an upper bound of what. So go ahead and solve interval 2. Oh, yeah, we'll do some math here, Taylor. Definitely we'll do it in about 10 minutes. Thank you so much, Taylor. It's really, chapter 19 is a tough one with the math, especially. What is the lower bound and the upper bound of this interval? What is the lower bound and the upper bound of this interval? So it's negative 50 plus or minus 10. Negative 50 plus or minus 10 would be what? Negative 60 to 40, right? Negative 60 to 40. And notice the interval does not contain 0. And then what would the, so we'll put a little wrong on this one. What would this interval be? This interval is going to be negative 10 through 210. And notice the interval contains what? This interval contains what value inside of it. And we're looking for evidence of a difference. So this would not meet the criteria of evidence. It contains 0. So 0 is theoretically the difference between the means. Does that make sense? Theoretically, the means might have no difference. And this would indicate theoretically the second mean might be the higher mean. It could be in this instance that the second mean is higher by 10. Now, we do estimate their difference to be 100, but it could be the case that the second mean like truly is higher by 10. We just, the variation in the data gave us a difference of 100, but there might actually be the second mean, the higher mean in this case. So really good questions right there. I think we're going to do one more from this. I think we'll probably circle back and do, which one is homework 10 question? Homework 10, we'll do long war after this. Which one is chapter 10 homework? Like, is that on the quiz also? Or it might be, it might be the man moves to a new city. So we might have two people, which is good. Definitely when people want the same question. That way multiple people can see it. And if it's the man moves to a new city is definitely one where notation is key. And you have to be careful like Brian, because sometimes we make math errors and those will come back to haunt us. So, it's large and small glass size. Here we go. So with this, it was chapter 17. Mm-hmm. So is it this one right here, the large and small glass size? So with this, we want to use the HAX method for solving it. So remember, it's not about solving this one question. I mean, Mark, you're welcome. Yeah, anytime. We'll do it. We're going to do Taylor's question next. We might circle back. 47. Do the man moves to a new city. Researchers investigated. So what is the first thing we do in the HAX method? The very first thing we do is we do what? What is the HAX method stand for? What is the very first thing we're going to do right here? I think it's going to follow us around this. What is the very first thing? Hypothesize, exactly. And so when we do this, if you gave people 2 glasses, what would you hypothesize about the amount of liquid they put inside the glasses? So just stepping through, and great job, Jesse and Sheena right there. If you had to hypothesize people get a small and a large glass, what would you think about the amount of liquid they put in the glasses? See, Jesse, great work right here. If you had to, you give people a small glass and you give people a large glass, what would you hypothesize about the amount of liquid they put in the glass? Without any knowledge. What would you think? So you're going to say, put liquid in this glass. So, but remember, the null has the equal sign. Now, we might see if there's evidence people put more liquid in the large glass. But so the null is a starting belief with no knowledge of the world often. Often we say that things are equal. It's a starting position that we can test if the null is true. We can see if there's evidence via our data that it's not true. But we're going to say that these two things are equal right here. Now, you might say, well, wouldn't people put more liquid in a bigger glass? But the amount of liquid put on average in a large glass is probably about the same as the small glass. We would want to see if there's differences. So people were randomly given either glass. They're invited to pour as much as they wanted. Did the glass size change the selected portion? So what are we investigating? That people put more in the large glass, people put more in the small glass, or they put different amounts in the glasses. So the researcher always sets what the alternative is. So are we testing, do they put more in the large, more in the small, or do they put different amounts in the glasses? Different amounts, exactly. And so when we do this right here, the null will always have the equal sign. The alternative will be based on the researcher's question. And we're testing here if they are the same and seeing if there's evidence that there's different. Now, I do want to point out we went through a really good steps on this earlier. So I'm kind of doing it. I always do each question kind of differently because that way we can have different methods of teaching. But here is basically all the notation. If you notice, we're in chapter 17 where we're doing the parameter of testing. The parameter we're testing is the difference between two means, and we are hypothesizing that the difference is 0. So you see right here, let me remove the green because that might not be, that was for the end of the problem. So these are what go with each other. If you use the green here, use the green here. If you use the blue there. If you use the pink there, use the pink here. And this is the parameter we're testing, the difference between two means, and this is the hypothesized value. So let me write that below it. Oh, that's not the hypothesized value. That's the parameter we're testing. Parameter testing just means the thing we're interested in understanding. We're interested in understanding the difference between the means. Hypothesized value is what we believe it to be if the null is true. This is the hypothesized value, sure. And knowing this right here and knowing what goes where is very important. And then knowing when we write the alternative, we just change the equal sign is going to help out a lot. And these are the tests right here, the t-test, the proportion test, and the two-sample t-test. Everything but the chi-squared is on the screen right there. So we should have that one right. And now we have to find the t, and then we're going to find the p-value. So the t statistic here is a standardized difference. So we have to take our data, and this is the annotate notation part. And it doesn't give us one thing, I think, or does it? It does not. What are we missing? I need 2 letters in the chat. We are missing one last thing here, which is going to be very important to solving this question. What are we missing? We do not have all of our notation. We are missing one super important thing right here that we will not be able to solve the question with. We have the sample sizes. Sample sizes are first thing right there. This is annotate notation. Well, we know it's quantitative data. Good question here right there. Yep, 100 points. It is quantitative because we have means, and Mr. T is mean if you're doing drugs. So that's going to mean we're doing the 2-sample t-test. But what are we missing? And I'll give a hint over here. What are we missing currently to know the shape of the t? What are we missing currently to know the shape of the t? We do not currently know the degrees of freedom. Great job, Kristen. So we need to go over to calculate Welch's degrees of freedom. If you're wondering where I'm at, great job, Jesse, right there. Oops, I can't type in the chat apparently. There we go. Mubot's going to put the apps in the chat. You want to go to student T when you go to the apps page. And then you want to go over here to calculate Welch's degrees of freedom. We take the information. We have sample size 23 and 27. 23, 27. And with respect to that, standard deviation 1.76 and 2.76. And degrees of freedom are 44.707. And we're going to find the p-value here in a moment. Okay. So now we know which t we are using, which is very important to solving this problem because it changes the shape. Notice here, it is all different t's depending on your degrees of freedom. So make sure to enter in the right degrees of freedom right there. So now we have the notation annotated and we know the degrees of freedom. So df equals this. Perfect. And we would check the conditions next before solving for the p-value. And checking the conditions are going to be random 10%, and then we pause. It's not a condition, just pause. And this is where we say it's going to be quantitative data. So since it's quantitative data, the third condition is nearly normal. And then the last condition right here is independent means, which means the amount people put in each glass is not influenced by the other group. So they're going to be independent and random right there. Everything looks to be met. The solving for the p-value is usually the tough part for people, but we are just going to take the information up here and put it into the equation. Now, you do have to check problems you solve to make sure you see how they're going to do the minus. It says where the population mu1 is the small glass. Okay, so this is mu1 over here. Just to make sure you know, this is mu1 ideas, this is mu2 ideas, and we'll copy paste that over here while we're solving. And now we go in, put the data right there, and now we go ahead and solve for the t statistic. Now, this is not the t star, that's for a confidence interval. This is the t, which is going to be a difference standardized. So the difference standardized is going to be the difference between the means, which is y bar 1 minus y bar 2. And then the standardization of it is going to be from the standard error. And the standard error is going to be S1 squared over N1 plus S2 squared over N2. And that's the quantity of the standard error. So now we're literally just going to take our numbers and plug them in here. And the difference between the means is 5.12. Remember, we doing the first mean, second mean, like that. And 6.54. Then we plug in the standard deviations. Standard deviations is 1.76, 2.76. Sample size is R, 23 and 27. There we go. Okay. 1.76 squared divided by 23. Good. Copy that. 2.76 squared divided by 27 plus this right here, square root, and that is the quantity of the standard error. So do not, I'm going to write this, but you want to carry all your decimals. And then we're going to subtract the difference up top for negative 1.4232. There we go. I believe so. Okay, let's take this and do 5.12 minus 6.54. There it is right there. Divide by 2.2, negative 2.2. So if you did the last problem with us, the p-value is going to be a little bit bigger here. And you always want to try to draw these out a little bit to see where you landed. So we landed over here at negative 2.2. And then we're going to shade to the outside of it. Then, because it's the does not equals test, we reflect it on the other side over here. And we would get double the p-value. So remember, it all goes back to the start of the question when we did the does not equals alternative, which I should write out here that mu1 not equal to mu2. And the does not equals alternative is going to be the key right here when deciding how to shade the curve. So because we chose the does not equals alternative, we're going to shade the curve the following way. P-value is about 3%. So we can take a guess at it if we want. I do like to guess the p-values to see how close we get, negative 2.2. As long as this is correct, we should be good. That is correct. And so the p-value to 4 decimals, that is a really hard guess to make. Really hard guess. I get 2 guesses. Why not? Really hard. Oh, wait a minute. I didn't put my 0. Oh, wow, there we got it. Wow.
Wow.
Well, wow. Okay. Well, let's show how to get that. Okay, so we go over here and we go to the app. I've done a lot of these problems, it seems. And we take our value, we put the negative version down here, and then we put the positive version over here. And very important, round to 4 decimals. And I was close enough within the margin of error of the question to get it right. 0.03, I thought it was about 3%. The next decimal was a pure guess. Well, I thought it was closer to 3%, so I went closer to 3. And then the fourth decimal was just pure guess. But the further out you go on each decimal, the more of a guess it is for me. Like I knew it was pretty close to 3%. Make sure to go over here. When I press on the apple, it says 1x. Make sure you are going to the outside right here. I should be on outside. How's it showing it to me right? That's weird. I should be on outside right here. Sorry, it said above. We want to be on the outside right here. You want to go to the T applet. I'll go from the start as though you're on the normal. So you want to go from the normal to the T. Then on the T, you want to enter in your degrees of freedom, which I think our degrees of freedom were 44.707. Then you want to find a p-value using T. And then you want to click the outside test right there, because remember, we're shading the outside tails. So we are finding the p-value using the T. We enter in both of our values right here, negative and positive, and then we get to 4 decimal places right here. Does that make sense right there, Sheena? So that is going to be how to get the p-value right there. And then you want to make sure it looks like your graphic that you drew. I do highly suggest drawing these out because you're welcome. Great work. Try drawing these out yourself because you should know what it looks like theoretically. So when you make your picture over there, it looks like the picture you've created. So if you have been drawing these out, you'll be like, yeah, that kind of looks like it. I mean, the tails are a little thinner right there, but you see where it's at, where it's a little beyond -2 and +2. And then your picture looks like it, and you know you've done it correctly. So you don't want this to be magic where you enter in the numbers and you're like, well, what do I click? You know what you're supposed to get as a picture, and then you can line the picture up with the correct degrees of freedom and everything else. So really good work right there. It's a good question. And then we get to the final part, and we want to use our statements right here. Here's our p-value. So let's remember how we talk. My p-value of 0.0331 is less than my alpha of 0.05. This means I reject the null, that there is no difference between the amount of liquid people put in these glasses. I have a true difference. There is no true difference. I have evidence for my alternative that there is a true difference. So that'll be right here. We have rejected the null. The data is evidence for the difference, that they are different. Be careful. We are just checking for evidence of a difference right there. But once again, you do not learn enough by just clicking these buttons. You do not learn enough by clicking the buttons. Please try to write this out or say it out loud. My p-value of 0.0331 is less than my value of alpha of 0.05. This means I reject my null, that the difference between these is equal to 0. The true difference between these is equal to 0. I have evidence for my alternative that the true difference between these is not equal to 0. The more you practice writing these out and talking about them, the better it is when you have to do it on the test. So good work right there. And remember, write this out. Don't just click the buttons. And so yeah, let's do Taylor's question. There's me in the corner. A Long War. Chapter 19, A Long War. I think Sloan wanted 10. The last canvas content. Oh, man. We could do Long War and then last canvas content. It's on the quiz, Long War. Not that many for chapter 19. Okay. Okay, let's go check this out here. A certain story on a long war. Let's do it. And with this question, Jump is going to be the best help for us. So I highly recommend using Jump for this. And let's start right here. We could use the hacks method to solve it. Oof, look at all the stuff they're making us solve right here. We'll solve it all out. But open up Jump. Here, I'm going to open up Jump in the background. Download the latest Jump here in a few days. So Jump makes these questions a lot easier. By a lot, I mean half the time or a third of the time. Okay, so we're opening up Jump, and here's what you want to do first. In Jump, you want to go and open up a new data table by going to File, New, Data Table. File, New, Data Table. Now, don't click inside of it. Just let it be there. Now, go to the data table here and click on it and go to Copy to Clipboard. We're going to copy the data to the clipboard right here. Boop. Now it's copied, and hit Control-C or Command-C on your computer. Make sure it's copied. With the data now copied, go back to Jump and go to Edit paste with column names. Very important right there. Paste with column names. Now, this is almost what we want. Almost. We have to now go to tables, stack. Tables, stack. Under tables stack, double click both quantitative columns right there, and then click OK. Now we have the data the way we want. So we can double click this. We'll X out of that one because we don't need that anymore. The data is in jump the way we want. You could also type it in, but it would take a little bit longer. Good to see you here, Robert. And we're going to change this to site of injury. We'll change this to type of injury. And then we have the count of the data. I am double clicking these right here. If you double click, you can change it. You don't technically have to do that, but it's going to help with the interpretations to make better sense of this. So with this is the chi-squared test of independence. And when we run the chi-squared test of independence, it's pretty easy to write the null and alternative. Let's run the test and then talk about how to write the null and alternative, because that's the first thing they're going to ask us. Analyze, fit y by x. Now you have to make sure your data looks this way before you do this. So if you don't see red, red, blue, go back and check out how we got here. Analyze fit y by x. We're going to see if the site of where the injury is explains the type of outcome. So why is there a certain type of outcome? Well, maybe the site of injury explains it, and then you have to enter in the count into the frequency. Frequency just means how frequently things occur. Count is the same thing, like how many count of observations do we have. Make sure it looks this way with red, red, blue right there. If it doesn't have the right colors or you don't put everything in, a lot of people forget the count, you won't get the right output. If your bars look completely horizontal across, then you didn't put in the count into the frequency. That's a very common error I see. Now, if you look right here, what is very clear? In this lung war, when people were hit in the limb, that's where it was often what? Or more likely to be what? What is just clear by looking at this? And you can see it over here in the data also. When people were hit in the limb, it was more likely than not to be what? There's the percentages. This blue region is the not fatal. People hit in the limb were what to have a not fatal injury? So people hit in the limb right here were more likely to what? So if we look at it, we're like, okay, these are people hitting the head or the neck. And you can see the percentages there, 93.18 for that over there. These were people hitting the body, 92.19 for fatal over here. And then you can go up here and hover over this and see people hitting the body, which represents, I think, 5 observations. There were 5 individuals, there they are right there too, who had not fatal injuries that were hitting the body. And it looks like there's a pretty strong association. Now, on the test, definitely go through the notes. There's a lot of examples in class on this. You might get a table like this. These are the counts of observations. So when we solve for this, on the test, we might ask you to calculate the expected value of a fatal injury, the expected amount of fatal injuries to the body. So let's do a few problem questions right here. And let's say, calculate the expected amount of fatal injuries to the body. So take a moment right here if you're watching this and try to solve this. This is a very good type of test question that we could ask you. Yeah, amount works. So how would we do this right here? So we want the expected count for this one. So there's a formula for this. The formula for this is going to be, what is it going to be? If you look right there, the row total times the column total over the grand total is going to give us the expected count. So we can solve it out pretty quickly. You can kind of point in on the cells, which is really helpful right there. So let's solve it out. Now we can do this for all of them, but here's what's great about jump. If you click here, you can just find out all the expecteds like that. And there's that 50.94, which we just found a moment ago. And jump carries even more decimals, or I guess that's rounding that right there. So jump just found all the expecteds. But now, these are really good questions. So if you're reviewing for the test, I highly suggest watching this video right here. Calculate the chi-squared. Cell chi-squared. So let's go back to jump. Let's take our output right here. Now we're going to calculate the cell chi-squared. These are test questions all the time on the test. So now we have right here. So the cell chi-squared is the observed minus the expected squared over expected. So we have to take the observed minus the expected, square that difference so it's positive, and then divide by the expected to standardize it. So when you plug in the numbers, what do we get? And let's try it out right here. 1.27, 1.28. But here's the thing. Once again, jump can help us out a lot right here by taking and just finding these cell chi-squareds, and there it is right there on the screen, carried to all the decimals we needed. So what's really great about this is jump does a lot of the work for us, and then we just have to understand what we are doing and what this all means. So jump has given me all the numbers I probably need to solve this question, but now let's talk about the null hypothesis. And so I'm going to pause here and I want someone in the chat to answer. What do we do when writing the null hypothesis for the chi-square test of independence? All you need to say is what of what? What word do we put between these, and then try reading it as a sentence? And you will have done the chi-squared test of independence. How do we do this for these problems? Anytime we want to interpret the null hypothesis for the chi-squared test of independence, the null hypothesis will be what? What will be the null hypothesis? So we just put one word between them. And you just read it. The site of the injury someone has is independent of the outcome or the type of injury they have, whether it's fatal or not fatal. That means it would not influence the lethality of an injury wherever you're hit by the injury. So that's very important right there for the chi-square test of independence. And you can see right here, the site of injury and whether or not it was lethal are independent, and the alternative is simply not independent. I like to put it between to say like site of injury is independent of whether or not it's lethal. I prefer to do it that way. Now we have the expected counts right here. So we're just going to literally have our jump table open and make sure to put things in the right spot. If you notice, we have the values of the expecteds right there. How many decimals do we need? 2 decimals. So mine, body, head, limb, not fatal, fatal, not fatal, fatal. So make sure to put the values in the right spot. If you're a little worried that you're going to see extra values, you could turn off everything but the expecteds. Do remember, you might have to calculate these by hand, so I would know how to calculate them by hand. And we just did a few of them a moment ago, calculating the expecteds or calculating the cell chi-squareds. Know how to calculate these values. There we go. There's the expected counts. Next, we get what is the chi-squared test statistic. Now, jump is going to find this for us, but there's an important concept we need to know about this. When we do the chi-squared test statistic, the chi-squared test statistic is the sum of all the cell chi-squareds. So what's 6 plus 24 plus 4 plus 5 plus 1 plus 1? It's 42.374. And just in case you don't believe me, these are all the cell chi-squareds. 1.27, I'll carry to 2 decimals. 4.97, 1.02, 3.98, 6.35, and 24.77. And we get 42.36 because I didn't carry all the decimals. But once again, the sum of all the cell chi-squareds is the chi-squared test statistic, 42.37 right there. So 42.37. How many degrees of freedom does it have? I wish I could appear on the screen for this because this is one of my favorite things to do. Since this is a 2 by 3, so when you look at this table right here, it's a 2 by 3 table. 2 by 3. 2 by 3. Is there a video that explains chapter 17 homework? Yeah, we've been working on it today. I think we did it during class, right? 2 by 3. Reduce each one by 1. 1 times 2. And that's the answer for the degrees of freedom. The formula is rows minus 1 times columns minus 1. And so you just reduce each one by 1, and you would get 2 degrees of freedom. The jump output's going to tell you this, but it's good to know how you get these degrees of freedom. Rows minus 1 times columns minus 1. I thought we did the quiz. We did a homework today, and a lot of the homework is like the quiz. If you have a specific one, let me know. Be like, can you work this problem? And we'll work it out. Now, we can find the p-value by hand, just like the t-statistic. We go over to the applets over here. We'll drop the apps in the chat. And we go to the chi-squared. The degrees of freedom tell us the shape once again. So we need to select 2 degrees of freedom. And now we're going to find a p-value using the chi-squared. And we're just going to drop the chi-squared value in. And if you notice, the p-value is basically 0. It's neat that you can actually get more decimals on this. This is scientific notation. So it's a very, 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 very small p-value. It's basically 0 as for all intents and purposes. And the jump output's going to show you this too. Down here, you can see the p-value right here, and the Pearson has it, is basically 0. I'm going to see if it calculates the same way. 6.29 e to the negative 10. And I think we got the same thing. And then looks like we're a tiny bit different, but it might be because there's more decimals, jumps not showing. So the p-value is basically 0. And what should be concluded? Well, we are going to reject the null hypothesis. Let's go back to our notation on this. With my p-value of basically 0, which is less than my alpha of 0.05, this means I reject my null that the site of injury is independent of the outcome. I have evidence for my alternative that they are not independent. So we reject the null at the 0.05 level of alpha, and we conclude that the site of injury or whether or not it was fatal are not independent. We have evidence that they are not independent. Yay! Really good question right there. So the big thing about these questions, and we're going to do the Canvas content next, drop any more questions in that you have. The big thing about these is we can use jump to solve a lot of these, and then we have to know what we are doing. So these are all the quiz questions. A lot of them can be done inside of jump right here by just bringing the data over and then solving using jump. So I highly suggest doing it and solving with jump. Just to show, we can go right here to copy to clipboard on this one. Copy it to the clipboard, bring over here, drop it in, paste with column names, table, stack. This is the same methodology for the one we just did. And then let's go here to region. I'm going to rename that so I can actually see it. And there's the label. Analyze fit y by x. We'll see if the label, we'll see if region explains label. Hey, what's up, Angie? We're going to do the Canvas content next. And there's the analysis of it. And so let's bring this on the screen with this so we can see what's going on. And now that we have the results, the null hypothesis would be that they are independent. The region is independent of label. So political party is independent of region. The chi-squared test statistic right here is going to be found down here on the bottom. The chi-squared test statistic is from the Pearson. Remember that the Pearson has your p-value. So it's 2.562. And then the p-value here is 0.6, and it wasn't want to 4 decimals. There we go. And that's a very high p-value, so we fail to reject the null. There is not sufficient evidence, and we should be good right there. This is how you want to understand the problems because, remember, we're trying to find p-values using the chi-squared and go through the last problem step by step to see how we're solving it and what we're doing. This one didn't ask us to find the expecteds, which wouldn't be a bad thing to solve for. Remember, you should know how to solve for all those values on the test. So whenever you have the chance, try to solve for an expected. Like, what is the expected amount of Democrats from the North? Well, once again, to do this trick on how to solve it, expected Democrats from the North, I will throw 5,000 points. If anyone in the chat right now can tell me how many Democrats do you expect from the North? And I'll even give you some hints right here. So we're talking about this cell right here. How many Democrats do you expect from the North? How many Democrats do you expect from the North? So remember, it's row total times column total over grand total. Well, 21 is what we observed. 21 is how many we saw. That is the count. So 21 is the count. That's how many we saw. That is the observed count. So when we do the formulas and we use observed, the count is the observed. So how many do we expect, which is E? So I've got remember it's row total times column total over grand total. So row total times column total over grand total. So if the question said, how many Democrats do we expect from the North, what would be the answer? We've got the equation written out right here. Well, 21 is what we observe. 21 is what we see. I don't think it's going to be exactly 20. I could be wrong. It might be 21. So remember, the equation is row total times column total over grand total. Is it 24? And then make sure to carry all decimals. So make sure to carry all the decimals, though. Is it 24? Usually it's not an exact number. So the expected will always have all the decimals. So it's going to be, let's see, 65 times 75 over 201. There, and then up and make sure. Great job, Andrew, right there. Let's show you the points. 5,000 points. Great job. And we should know how to solve these. That's the expected. And then we can get it really easy in jump by just going there and getting the expecteds. Now, the cell chi-squared is the difference squared. So we can take the difference right there, square it, divide by this, and that's the cell chi-squared. And then we can confirm our answer right here by going to cell chi-squared. And look, there's the same answer. So knowing how to get these numbers, knowing how to get cell chi-squareds is going to be very important. That it's the observed minus the expected squared over expected. And the more you practice these types of questions and know what you're solving for, the better you can do on the test, because there are questions about, how do we get the chi-squared test statistic? It's the sum of all the cell chi-squareds. What is the null hypothesis for the chi-square test of independence? It's that they're independent. The alternative is that they're not independent. And independent means not associated. Not independent means associated. So lots of really good questions in this. Like, we could do a lot of these. But if you notice, they're very similar. But a lot of them are best done with jump. Suppose we conducted a test of independence and we rejected the null hypothesis. What would we conclude? We conclude there is an association between the two variables. Wait a minute. Suppose we can conduct a test of independence and end up rejecting the null. Which of the following conclusions is appropriate? The two variables are not independent, so one variable depends on another. Really? This is very interesting, my Pearson. So one variable depends on the other. I think this is what they're going for. Really? Why do they not like this? The two variables are not independent. Don't like this question. I might even eliminate it. I often say there is an association. That's why I went to this one first. The null is that the two variables are independent. We have rejected the null hypothesis. Which of the following conclusions is appropriate? I guess they're going for very specific wording to say one variable depends on another. Yeah, because like dependency isn't a type of association, though. I don't know sometimes who writes the questions. I'm actually going to delete this question. I hate it that much. So we're going to do Canvas content next. I really don't like that. I think that's very confusing for students, and I really don't like it. No, sir, I don't like it. So let's go to replace this question. It's just I don't know exactly what they're getting at right there. Comparing counts. I'm going to replace it. 2 seconds. Now we'll do a new question right here. So many questions to pick from. 45. Try to pick a very similar type easy one, a true false. Okay, this is a good one. good review. I feel like we need maybe more of these though, because we only have like 6 questions. RA4, I think we'll pick. All right, cool. Replace question, and then we'll do canvas content. Okay, I think we got it done right there. Have you done chapter 17 homework number 8 and 9? We might have. Which ones are 8 and 9? The core plus? Wait. We do the let's do the canvas content. And we might have time for 1 or 2 more. Let's hop over here to canvas content. We did the core plus mathematics in 1 class, I know. Let's do the last canvas content. Yay, you're welcome, Taylor. That's what I wanted. That's why I like doing... They're all kind of, if you notice, they're all kind of similar. They're best done with jump. You can do them all by hand, but it takes a lot of time. Knowing the jump output and then doing some practice solves is very important. Thank you, Taylor, for asking that right there. Let's do the chapter 1917. Okay, 125. Let's check out the canvas content. Here we go. So we'll do 2 versions of this, and then we'll do a few more questions right here. The results of a chi-square test of independence concludes color and choice is dependent. Ooh, we see we're using those words, are we? Yeah. On the gender of a kindergartner. Which of the following is true? Now, the alternative is dependent. So what officers, I think we did it on Thursday last week. Check out the officers there, and I can link it here in a moment, Angie. Good question. The results of the chi-square test for independence conclude color and choice is dependent. So what does this mean we've done? So what have we done if we conclude things are dependent with the chi-square test of independence? So remember when we do the chi-square test of independence, remember what we start with? Site is independent of type of injury. So if we were to conclude that it's dependent, we've definitely done what? Yep. I can post the link to that one, Isabel, in the chat. We've done that one a few times now. What would this mean about the chi-square test of independence? What have we done? So remember, the null is that they're independent. So if we conclude that they are dependent, what have we done? So the results of a chi-square test of independence conclude that 2 things are dependent. So what does that mean we have done if the null is that they're independent? So that's kind of the key to this question, then we can find the right answer. We've concluded that they are dependent, but the null is that they're independent. So if the null is that they're independent and we have evidence of a dependency, we have rejected the null. And if we reject the null, then the p-value was lower than the alpha level. So that's how we reject the null. So this doesn't say reject the null, but it does say the p-value was lower than alpha, which means reject the null. So that's a really fancy way of saying we had the required evidence to reject the null for the alternative. The overall chi-squared test statistic is found how? So the chi-squared test statistic, which is found down here on the bottom, we'll show it again. What do we do to the cell chi-squareds? I did this earlier in a question. What do we do to all these cell chi-squareds right here to get 2.562? 2.562. How do we get the chi-squared test statistic? So here's all the cell chi-squareds. You know, so it says cell chi-squared right there. There's all the cell chi-squareds. How do we get the chi-squared test statistic for the Pearson chi-squared test statistic? How do we obtain that value? Good thing to know. We do what with all these values? what do we do with all the values right here? For the chi-squared test statistic, we what all the values together. It's also on the formula sheet. What do we do? Might have a typo or two in here already. With all these values, we what them together. Then we get the chi-squared test statistic. There it is right there. So we take all the cell chi-squareds, which these are cell chi-squareds, and we add them together to get the chi-squared test statistic right there. So the sum, ooh, look at that. That's how I misclick. We add up all the cell chi-squareds to get the chi-squared test statistic. Chi-squared tests are used for a hypothesis test of the association between two categorical variables. That is the literal start to this chapter. And you notice right here, we have only categorical variables like someone's political party and the region of the US they're from are both categorical. We have right here the site of where they got injured and the outcome of the injury. Count is just the amount of observations in each group. A lot of times when you see us analyzing data, it's going to look more traditionally something like this over here, where we go to analyze fit Y by X, and we have here gender and whether or not someone's broken a bone. And we are using the chi-squared test of independence to say that there looks to be an association between someone's gender. Males were more likely to break bones than females. About 54% of males broke a bone. And over here, 40% of females broke a bone. It does look to be an association going towards males breaking a bone. So this is very true. Two categorical variables. And this actually goes to the condition called count data. We know count data is passed by two categorical variables. All else being equal, the further the t-statistic falls from zero in either the positive or negative direction, the more like it is there's a difference between the two population means is statistically significant. And this is very true. And I want to point to two tests we've done today. So let's take this right here, and then we could find the other one. Where's the other one at? The other test, I believe, is not that one. It's right here. So with these two graphics, we'll make this on one page here so you can see it. These were two tests we did earlier. And here's the other test down here. And the p-values were respectively about 1% and 3%. So over here, we had a p-value of 0.011, and here we had a p-value of 0.0, really color changing, I do that to me, 0.033. That's the amount of area underneath the curves in the outside region. Now, if you look right here, you'll notice that on this one, we landed closer, just a little bit closer to zero. So we're not as far away from zero, and the p-value is bigger. Over here, we landed further away from zero. So since we're further away, the p-value is going to be smaller. And you could think theoretically on this, if you land really close to zero, like let's say hypothetically, we had a difference that was a t-statistic of like negative 0.4, well then we would have done the following. We would have graphed at negative 0.4, and negative 0.4 is about here. And so that's good enough. We put the straight line for that one, and then we do the dashed line for the just as extreme. And then if you notice, the p-value is going to be a lot bigger. Now the p-value is the majority of the curve right here. So the closer you land to zero, zero is where the null is at. So since the null is at the center, well, then what you saw was more likely, given the null is true, is p-value might be about something like 82%, just a guess right there, but a much bigger p-value when your t-statistic is smaller. So that's very, very true right here, and understanding it theoretically is important, not just clicking the true or false. They would say what falls from zero. So the further we fall, the more likely it is it's statistically significant. That is correct. Below is the jump output, and I really like this right here because it gives you everything you need to know, and this is how the jump output often looks. So if you look at this output right here, we could go over here to jump, and let's go ahead and take a look at it. Analyze fit Y by X. I'm just making similar output, gender, and looking at people's high school GPA. And you'll notice this output in the t-test is just the same way it looks on my Pearson or on Canvas right there. So there's the t-test on Canvas, and here's the t-test on Jump. Now we're trying to find this t-ratio right here. The t-ratio is the difference standardized. So the difference is y bar 1 minus y bar 2. Yeah. Yep. Covering Canvas Counter. Thank you for asking. We've been trying to do everything in order right here, doing all the new things we can. And then the standard error of the difference is going to be square root s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. And that's the standard error. And so the equation to find the t-statistic is literally, so remember we got all that right there, the difference and the standard error. The equation for the t is that the t is equal to y bar 1 minus y bar 2 over standard error of, which is standard difference. And so there is the standard error of the difference. Notice this is the difference, and this is the standard error of the difference. So all we have to do is divide those numbers. So we could see here in this example, which we already have the answer for, if we take 0.14985, negative version, and divide by 0.02770, we get the number right there. So the same work could be done over here on our problem, where we take the difference, which is just y bar 1 minus y bar 2. So that's the difference. Then we divide by the standard error, which is 7.79, and that's already found for us. Standard error of difference is that quantity. So 63.76 is going to be the standardized test statistic right there. Round to 2 decimals, and we should be good. And submit the quiz. We'll do another version right here. And that's got it. We'll do another preview of it. In the chi-square test of independence, large values of chi-square test statistics indicate a cause and effect. No. These words right here in statistics are not used, but it's important to know that larger values of chi-squared, like when you land at a chi-squared of 1 versus 2 versus 3, the p-value will get smaller. So we'll bring it up here to a bigger curve, and we'll reduce some decimals so it doesn't look crazy. The larger the chi-squared, the smaller the p-value. So I'm increasing the chi-squared, and we always do the area to the right. You'll notice that the chi-squared is a right-tailed test. Deals with the chi-squared always being positive numbers because we're just looking at the differences right here. So probability greater than chi-squared, hence why we go above right there, because the probability greater than chi-squared. So here's the p-value in the jump output, and we could replicate this. You can see the decimals on it if you want. Or we'll do one we might actually be able to see. Hey, Jesse. All these p-values are so small that we're not going to see them. No, this one right here. Here we go. Degrees of freedom 4, because it's a 3 by 3, 2 times 2 for degrees of freedom. And so 4 degrees of freedom, 2.562. 4 degrees of freedom, 2.562. And there's the 0.6336, which we see in the jump output. That's the wrong output. The output right here, we see 0.6336, concluding that the Pearson has our p-value. So larger values of chi-squared give smaller p-values. They do not show cause and effect relationship. Thank you, Jack, right there. 100 points. Appreciate it. And that is true, right? Oh, that's false. I was thinking about the p-value thing. The overall chi-squared test statistic is found by adding up all the chi-squareds. The expected cell count frequency is based on the researcher's opinion. For 1,000 points, what is based on the researcher's opinion? What is actually, there's 2 things you could say are based on the researcher's opinion. What 2 things are based on the researcher's opinion? And I'll show you hints over here. What 2 things are based on the researcher's opinion? One of them is currently on the screen. What are 2 things based on the researcher's opinion? Expected cell counts or not? What is one of the 2 things based on what a researcher decides it to be? One of the 2 things that a researcher can decide right here. So there's not both of them on the screen currently, but something the researcher can pick based on what they want to test would be the sign of the alternative. The sign of the alternative is just what you want to test as a researcher. And last but not least, if we go to the very end of the question, what is also going to be picked by the researcher towards the end? Or they'll do it at the start, but then they'll use it at the end. So what would also be, so the sign of the alternative, and what else is also picked by the researcher? 2 things the researcher can pick would be the sign of the alternative, and then also their what? Do they pick their p-value? They don't pick their p-value. They can pick their alpha level here. Thank you, Jack, so much right there. I'll throw Jack 1,000 points for that right there. Really helpful right there. Appreciate it so much. Officer is going to the project, and there we go. They do not pick the expected cell counts. Which of the following is not a way to check the nearly normal? Oof. Let's see right here. And so some of these are pretty good right here. They're all actually pretty good. One of them is worse than the other. So histograms means look at the data. That's good. We can look at the data here. So if we pull up some data, analyze distribution. Let's just go to this data. It doesn't look normal at all. So we can do a histogram to look at it. So there's us looking at the histogram. The central limit theorem is the large enough n condition right there. So the central limit theorem states that as n gets larger, sample size gets larger, the distribution will be more normal. A goodness of fit test can be done by doing continuous fit to see if a fitting a normal works. The p-value comes back. It might be kind of highish for this. It is high, so we would not have evidence of non-normality, even though it doesn't really look it, probably due to small sample size. And the normal probability plot is going to be right here for the normal quantile plot telling us if it's normal. And actually, it does kind of follow the normal. Small sample sizes are weird. So the one that doesn't work is saying the degrees of freedom are greater than 10. That would indicate that the sample size was at least 11 for one sample t, which is not usually enough for us to say it's normal. Below is the jump output. What is the corresponding level of significance of alpha to the confidence interval? So when we do a confidence interval, this is a really good question right here. Confidence intervals and tests kind of coincide in what they do. The confidence interval is the inside. The two-tailed test is the outside. And so if we have something like a confidence interval that was done at 0.996 or 99.6% confidence, which would be even wider than that, it would correspond to the two-tailed test where there is, we could say 0.4 on the outside, but that's 0.004, and that's the alpha level. Alpha is usually expressed as a decimal. So if you notice, these two values are just complements right here. Be careful how you express them. And the way to know this easily right here, so we can go over here and it says, what is the corresponding level of alpha? Confidence level right here. I was looking at the wrong one. Confidence level right here is this. So we just take and do 1 minus. There we go. And it wants for the confidence interval. So there we go right there. Just the complement is the outside. And it's the corresponding. We should be correct. And we did it. Good stuff. Let's see right here. And we've done the two city one. So I might put that up right here. And I might post it in the chat. The two cities. Got to grab some lunch here in a moment. Let's see here. Man moves to two cities. Two cities. A man moves. Probability part 2. Oh, man. A man moves. May 1st. Here we go. December 5th. Here, we'll use an old video. A man who moves. Oh, my gosh. Check it out. Here we go. So that is what I need to shave right there. And so let me copy this into the video chat right here. There's a different version of me solving it right here. Kind of like how I wrote that out. I think I used the formula sheet for that. I should do that more often. So good job, Brian, right there. Last year, December 5th. So this is a really good problem. Going through the notation is going to be key right here. Highly suggest practicing your notation, marking the notation, knowing what you're solving for is going to be key right there from Bearded Brian. How'd you figure out the p-value again if you're given the difference from the... so it was on Canvas content? Well, it might be a missing p-value thing. So I think I know what it is. Let me see if I can show this right here. So if we have, where's my Canvas content? So if you're working the Canvas content, we got to go back and pull it up. Do you have other p-values, Sloan? Do you currently have other p-values? No worries. Do you have any of the other p-values? Like, is one of the p-values missing? Like, does it show you two of the 3 p-values? We'll go back to Canvas content. You only have one p-value. Let's see if I can find it right here. Probability less than t. So what would that look like? Okay, so you have one of the p-values. Let me show it right here. And you have probability less than t, right? So you have prob less than t. And what percent is that? What decimal is it? And what how much is it? So that's going to be all the way over here. And that is equal to So what is this amount going to be over there? Could have drawn it a little bit better. What is this amount going to be right there? And then are you looking for the greater than test? You're looking for the difference? So how do we get the does not equals test? To look very similar. So what would that p-value be? So this is the less than, this is the greater than, and then this is the does not equals right there. So how would we find, we want to find, so this is the answer for the p-value there, p-value here. And now we want to find, well, if we add them both up, what do we get? If we add up both those values, what do we get? So does that look like 100% of the curve? Like if we say this is equal to this, does that look correct? I think you'll see it. I agree. You're on the right track, Sloan. 1,000 points. Keep it up. So what do we do to get the does not equals test? The p-value of the does not equals test is what? You're right there. We've got some drawings now. So what do you get when you subtract that from that? So does this look like, does that look like that much of the curve right there? What does this look like to you? What does it look like has been done here? And we'll put in some fake numbers here. These are fake numbers. So these are fake numbers. Once again, these are not real numbers. What does it look like has been done to the area from the second curve? Basically, I want you to see it and be like, oh, I get it. Well, did we split it? So should we do the following? Is that what it should be right there, you think? And I'll show it on the applet here in a second. I think you're right there from seeing it. Well, but it's too, well, this area, here's a hint. This area right here is the same area right here. Those are the same. Those are equal. So the answer has to be more than this. The answer has to be more than that. But this area over here is just a reflection of that area on the other side. That's the big hint. So this area, all those areas right there that I've circled are the same amount of shading. That's the big hint. That's correct. Yep. It's just times 2. Because when we do the does not equals test, we shade on the other side just as extreme. So if you look over here at the applet, we'll go to the apps. Yep. And that's why I want you to see it to be like, oh, okay, the does not equals test is like shading both sides of the curve. What's actually cool is that Jump actually has a p-value animation for you. I guess we have to do the analyze distribution age, go over here, do this, and then we can do the p-value animation. So test mean, Want to do 19.52. Something in the interval so we get a p-value that's viewable. And then we go right here to p-value animation. And you can go right here and you can see it where we do the lower than p-value, the higher than p-value. Notice we're just going to double this. Yeah, that you're welcome. That's exactly what I love to do. That's the big thing. And notice the two-tailed test. See how the p-value here is 0.0494. The two-tailed test is going to be like 0.988, right? 0.988, I think. 0.90988. So all I did was double that number in my head because it's just going to, and now you can cut it in half to get this, or do 1 minus to get this. So basically 95, 5%, and basically 10%. So really important right there to understand it and to see what's going on with it. We could like work with this and get something. So we want to go a little further away, or a little further away. Not that far away. Oh, it rounded or whatever. Yep. So really great stuff right there. And I'm going to grab some lunch. I'm going to reset the camera. Till then, bye for now, everyone. Bye.